Hey, welcome back, everybody. Today we want to show that e to the I n theta is equal to cosine of n theta plus I sine of n theta for all natural numbers n. And so in order to do this proof by mathematical induction, we're going to need to recall some important facts. So one, we've got the cosine of the sum of angles formula here. You know that from pre-calculus. Two, we've got the sine of the sum of angles formula. We know that from pre-calculus as well. And then three, we have Euler's formula, which we proved in a recent video. Quite a superstar. And so, yeah, why do I know that I have to prove this using mathematical induction? Because really, this is a proof involving a sequence of statements, right? For every natural number, I get another statement involving natural numbers. So, yeah, it's going to be a proof by induction because I'm going to have a sequence of statements involving naturals. And so, again, we want to show for all natural numbers n, e to the I n theta is equal to the cosine of n theta plus the I sine of n theta. Remember, I here is the square root of -1. And so let's start our proof. So I'm going to say let P of n be the statement. E to the I n theta is equal to cosine of n theta plus I sine of n theta. And so let's start with a base case. So that'll be n equals 1 in this case. And so let's see what we have here. So this will be, really, this corresponds to the statement P of 1. So we've got e to the I. Well, if I plug 1 in for n, this is e to the I theta. This is equal to the cosine of theta plus I sine of theta, which we proved is true. This is Euler's formula. So this was previously established. And so now we move on to the inductive step. So let n equal some particular k. And we want to assume that P of k is a true statement. And we want to show that P of k plus 1 is true. So I'm going to say that is if e to the I k theta equals cosine of k theta plus I sine of k theta, then e to the I, well, k plus 1 theta is equal to the cosine of k plus 1 theta plus I sine of k plus 1 theta. Okay, so here we have a conditional. We want to assume P of k is true, and we'll use this inductive hypothesis to show that P of k plus 1 is true. So let's see what we have here. So we have e to the I k plus 1 theta. Now let's do some algebra. This is equal to, this is e to the I k theta plus I theta. But by algebra, we know that's exactly e to the I k theta times e to the I theta. And here's where we need our inductive hypothesis. So by our inductive hypothesis, this is exactly equal to this. And so this is equal to, so right here I'm using, again, the inductive hypothesis. So this is exactly the cosine of k theta plus I sine of k theta. And then e to the I theta by Euler's formula is cosine of theta plus I sine of theta. And again, maybe I want to put a little bit of a note here. So this is by the inductive hypothesis. And so now we're just going to do some algebra here. So let's multiply. So this will be cosine of k theta times the cosine of theta. Looks like plus I cosine of k theta times the sine of theta. And so now I'll distribute this to both terms. And we want to be careful, right, because I squared is -1. So carefully distributing gives us the following. So this gives us I sine of k theta times the cosine of theta. And then I times I is -1. So this is sine of k theta times the sine of theta. And I'm hoping, if you really, really think about it, that you notice something. So here and here, as well as here and here. Now, if you go back to our initial list in the recalls, do you spot these? Yeah, we have exactly those. Okay, so that's pretty handy. So I can repackage this into this. I can repackage this into this. Just realize that for us, you know, A is k theta and B is theta. And so now we continue. Let's see what we have here. Okay, so bringing those together, that should remind you of the cosine of sum of angles formula. So that's equal to the cosine of k theta plus theta. So those two terms together. And then here I'm going to factor out an I. And you should notice the sine of the sum of angles formula. But I could factor a theta out. So by algebra, this is the cosine of k plus 1 theta plus I sine of k plus 1 theta. Well, that's great. We've shown if p of k holds, then p of k plus 1 holds. So the first statement implies the second statement, right? So the important thing to note is that since k was arbitrarily chosen, it follows by mathematical induction that e to the I n theta equals cosine of n theta plus I sine of n theta for all natural numbers n. So end of proof.